So another type of optimization problem we can do is basically just a number problem. So in this problem, we have the problem to find two positive numbers x and y such that their sum is 20, and the expression x to the fourth y is as large as possible. So these problems aren't usually that hard. It's just sort of a matter of recognizing what the constraints are on the numbers. So what we know is that if the sum of x and y is 20, then that means that x plus y is equal to 20. And the thing about this is we could say that the quantity to be optimized is is going to be x to the fourth y, which is true. That is, in fact, the quantity to be optimized. It's sort of abstract. We're not talking about like areas of pig pens or picture frames. But it still has the problem that, you might think, well, therefore, when you write the objective function, why not just say that the function is x to the fourth y? And this just underscores the point that you can't do that because we don't know how to deal with a function that involves both x's and y's. I have to get it in terms of x. Fortunately, that's not that difficult to do because we can write y is equal to 20 minus x just based on this constraint. So this is going to be x to the fourth times 20 minus x, just replacing y with an expression involving x. So that's going to be 20x to the fourth minus x to the fifth. The feasible domain, we know that both numbers have to be positive, which means that I can't choose x. I can't choose x to be anything that's 0 or less. So it's going to have to be greater than 0. And if I choose x to be 20, then y becomes 0, which is not positive. So the domain is 0, comma 20, and not including the endpoints. So a little bit of a complication here, just because we can't treat this as a closed interval. So what we're going to do now is we're just going to optimize f of x on the interval 0 to 20, and then we're just going to have to separately verify that we've in fact found a maximum instead of a minimum. So let us calculate the derivative of f, which is 80x cubed minus 5x to the fourth. That equals 5x cubed 16 minus x when I factor it. So we can certainly see this is defined every place. We can find the critical number, f prime of x equals 0, when x equals 16. So x equals 16 is a critical point. So now what we want to do is, we know that if there is a local min or max, it has to occur at x equals 16 because that's the only critical point that we found. So let's verify that we've in fact found a max. Simplest way to do that, well, actually, let me point out what the two different ways you can do it are. You can do it for the first derivative test by evaluating the derivative at by evaluating the derivative on the left and the first derivative on the left and the right of the critical point, or we can go to the second derivative test. Let's actually do the first derivative test, and let's do them both, and both of them will show that we have a maximum. So what I can do is I can plug in any point to the left or right of the critical point to see if the derivative is positive or negative on either side. So let's do like f prime of 15 is going to equal 5 times 15 cubed 16 minus 15. So that's going to be 5 positive number times a positive number times a positive number. So that's going to be greater than 0. And if I plug in, let's say, f prime of 17, I'm going to get 5 times 17 cubed times 16 minus 17. So that's a positive number times a positive number, and then 16 minus 17 is negative 1, so that's a negative number, so that's less than 0. So what we can see is that the function is traveling up and up and up, then it gets to the critical number of 16, and then it's traveling down. We know that because of the sign SIGN of the derivative. So this is the first derivative test that shows, therefore, x equals 16 is location of a max, local max. I could have done this through the second derivative test, by the way, and I'll just show you what that comes out to. If I take f double prime of x, looking at the derivative here, I'm going to take its derivative. That's going to be 240 x squared minus 20 x cubed. It's a little hard to see just looking at this, but if I factor it and I get 20x squared, 12 minus, let's see, it's 12 minus x. What we can see is that if I take f double prime of 16, I'm going to get 20 times 16 squared times 12 minus 16. So that's positive number times a positive number times a negative number. So that's less than 0. What we can see therefore is that the function is concave down, such that the critical number 16 is sitting atop a concave down function. So once again we can see that therefore by the second derivative test x equals 16 is location of a max. So the answer, recall what we were being asked to find. We were being asked to find two positive numbers x and y such that their sum is 20 and x to the fourth y is as large as possible. The answer is going to be x equals 16 and y equals 4. How did I choose y equals 4? Because I know that x plus y has to equal 20. So there we go.